Tonight on ZZZcience, we'll drift together into the quiet corners of the universe. Whether your mind is racing or your body just needs rest, these gentle stories of science are here to help you slow down and drift off with ease. Galaxies are not static islands drifting forever apart. Over billions of years, they move and interact under the steady pull of gravity. When two galaxies come close enough, they begin a slow and graceful dance, eventually merging into a single, larger galaxy. These encounters can trigger intense bursts of star formation as clouds of gas compress and collapse, while stars themselves rarely collide directly. Gravitational forces reshape the structures of the galaxies and can even feed the growth of supermassive black holes at their centers. Our own Milky Way is on a collision course with the nearby Andromeda galaxy, destined to merge in about 4 billion years, creating a new, larger cosmic city of stars. Quasars shine as some of the brightest beacons from the distant past, powered by supermassive black holes. Quasars are luminous objects found in the centers of young galaxies, shining across billions of light years, fueled by black holes consuming enormous amounts of gas and dust. Quasars emit incredible amounts of energy, often outshining the galaxies that host them. Their intense radiation allows astronomers to study the early universe and the growth of black holes. Quasars serve as cosmic lighthouses, illuminating the intergalactic medium and revealing the conditions of the universe in its youth. Their dazzling brightness and immense distances make them among the most fascinating objects in the cosmos. In the universe's earliest moments, space expanded faster than the speed of light in a burst called inflation. Within a tiny fraction of a second after the Big Bang, the universe experienced an extraordinary event known as cosmic inflation. During this brief but powerful period, space itself expanded exponentially, growing faster than the speed of light. This rapid expansion smoothed out irregularities, making the universe remarkably uniform on large scales. It also stretched tiny quantum fluctuations into the seeds of galaxies and the large-scale structures we observe today. Inflation solves several cosmic puzzles and is a cornerstone of modern cosmology, offering deep insight into the birth and structure of the universe. The first stars ended the universe's long, dark silence, lighting up the cosmos for the first time. For hundreds of millions of years after the Big Bang, the universe was a vast, dark expanse with no stars to shine. Then the first stars, massive and brilliant, ignited, piercing the darkness. These ancient stars burned hotter and faster than most stars today, forging the first heavier elements in their cores. Their intense radiation began to rayonize the surrounding hydrogen gas, clearing the fog and making space transparent to ultraviolet light. This era, called Cosmic Dawn, transformed the universe from a cold, dark void into a vibrant, light-filled cosmos, setting the stage for galaxies, planets, and eventually life to emerge. High-energy particles race through space at nearly the speed of light, born from violent cosmic events. Cosmic rays are charged particles, mostly protons and atomic nuclei, accelerated to incredible speeds by some of the universe's most powerful phenomena, exploding stars. Known as supernova, and energetic black holes fling these particles across the cosmos at nearly the speed of light. When cosmic rays reach Earth, they collide with atoms in the atmosphere, creating showers of secondary particles. These energetic visitors can influence atmospheric chemistry and possibly affect cloud formation and climate. Though invisible and mysterious, cosmic rays connect us directly to the universe's most powerful events, Our galaxy belongs to a massive supercluster containing thousands of neighboring galaxies. The Milky Way is part of a colossal structure called the Laniakea supercluster, home to thousands of galaxies bound together by gravity, stretching over hundreds of millions of light-years. This cosmic metropolis is a sprawling network of galaxies moving together through space. Within Laniakea, galaxies interact, collide, and grow, all under the immense gravitational pull of this supercluster. Understanding our galaxy's place within this vast community helps astronomers comprehend the large-scale structure of the universe and the forces shaping it. Vast empty spaces, known as voids, stretch across millions of light-years between galaxy clusters. Between the dense clusters and filaments of galaxies lie enormous cosmic voids, immense regions with very few galaxies and very little matter. These voids can span tens of millions of light-years and influence how galaxies move and cluster around them. Though nearly empty, voids contain some sparse gas and dark matter. Their existence shapes the large-scale structure of the universe, carving out the cosmic web and affecting the dynamics of cosmic expansion. Studying voids sheds light on cosmic mysteries like dark energy and matter distribution. Nearly invisible neutrinos pass through everything, including your body, all the time. Neutrinos are tiny, nearly massless particles created in vast numbers by the sun, exploding stars, and other cosmic events. These ghostly particles barely interact with matter, passing through entire planets, including Earth, without being stopped. Trillions of neutrinos fly through you every second, silently connecting you to the energetic processes of the cosmos. Detecting them requires massive, sensitive instruments buried deep underground or under ice. Though elusive, neutrinos offer unique insights into stellar explosions, the sun's inner workings, and fundamental physics on the largest scales. The universe looks remarkably uniform in every direction. When viewed across vast distances, the universe appears surprisingly consistent. No matter where we look, the distribution of galaxies and matter shows no favored direction. This cosmic isotropy, paired with homogeneity, means the universe looks much the same everywhere on the largest scales. This principle underlies much of modern cosmology, simplifying our models of the universe's evolution. Observations of the cosmic microwave background strongly support this remarkable large-scale uniformity, hinting at deep and fundamental symmetries in nature. A sea of ancient neutrinos fills space, relics from the earliest seconds after the Big Bang. Almost instantly after the Big Bang, the universe was flooded with nearly massless particles that barely interact with anything. These neutrinos decoupled from matter within the first second and have been streaming through space ever since, forming a cosmic neutrino background. Unlike light, these particles pass through almost everything unimpeded, making them extremely difficult to detect. Despite this, their existence influences the evolution of the cosmos and the formation of large-scale structures. Detecting and understanding these relic neutrinos would open a window into the universe's earliest moments, offering insights into physics at the dawn of time. Scientists measure the universe's expansion rate today with something called the Hubble constant. The universe has been expanding ever since its fiery birth, and the current rate of expansion is described by the Hubble constant. This value links how fast galaxies are moving away to their distance from us, providing a kind of cosmic speedometer. However, measuring the Hubble constant precisely has proven difficult. with different methods giving slightly different results. This tension in measurements fuels ongoing research, because knowing the exact expansion rate helps us understand the universe's age, its size, and its ultimate fate. The Hubble constant is a fundamental parameter in cosmology, anchoring our understanding of cosmic history and expansion as galaxies move away. Their light stretches to longer, redder wavelengths, a phenomenon called redshift. As the universe expands, galaxies drift away from us, and the light they emit is stretched into longer, redder wavelengths. This effect is similar to the Doppler effect with sound, where a siren's pitch lowers as it moves away. Redshift not only tells us that the universe is expanding, but it also helps astronomers measure distances to faraway galaxies, allowing us to look back in time. By analyzing redshift, scientists can piece together the history of cosmic expansion and understand how the universe evolved over billions of years to measure vast cosmic distances. Scientists use a step-by-step method known as the cosmic distance ladder. Measuring distances in the universe requires clever techniques because objects are far too distant for simple tools. Astronomers rely on the cosmic distance ladder, a series of interconnected methods, each building on the last. They begin by measuring distances to nearby stars using parallax. Then they use standard candles, such as Clifford variables and supernova, whose true brightness is known, to estimate farther distances. This layered approach allows scientists to map the universe's vastness with accuracy, helping us understand the scale of cosmic structures and the timeline of the universe's evolution. The cosmic horizon marks the farthest edge of the universe we can observe, beyond which lies the unknown. Because the universe is about 13.8 billion years old, light from beyond a certain distance has not yet had time to reach us. This boundary, known as the cosmic horizon, defines the observable universe, the sphere around us that contains everything visible. Beyond this horizon may lie countless more galaxies and mysteries, but they remain forever beyond our reach. As time passes, the horizon expands slightly, unveiling more of the cosmos. Yet the cosmic horizon reminds us of the limits of our knowledge, urging humility and wonder as we continue exploring the universe. Tiny grains of cosmic dust drift through space, playing a vital role in forming stars and planets. Cosmic dust consists of microscopic particles made from elements like carbon, silicon, and metals. Although these grains are incredibly small, they play an outsized role in the universe's life cycle. Within dense clouds of gas and dust, gravity pulls matter together, and dust helps cool the clouds by radiating heat, allowing them to collapse further. This process leads to the birth of new stars. Around young stars, dust grains collide and stick, gradually forming planets, moons, and other celestial bodies. Dust also provides surfaces for complex molecules to form, fostering the chemistry essential for life. The universe's first stars were nearly pure hydrogen and helium, without heavier elements. The earliest stars, known as population 2 stars, formed from primordial clouds made almost entirely of hydrogen and helium, the simplest elements created in the Big Bang. These stars were massive, burning hotter than most stars today and producing intense radiation. They lived short, brilliant lives before exploding as supernova, dispersing the first heavier elements like carbon, oxygen, and iron into space. These heavier elements became the building blocks for later generations of stars, planets, and eventually life, while none of these first stars remain today. Their explosive deaths shaped the chemical richness of the universe and set the stage for everything we now observe. Hidden behind cosmic dust, distant galaxies glow brightly in infrared light. Many galaxies far away are cloaked in thick clouds of dust that block visible light, rendering them invisible to optical telescopes. This dust absorbs energy from intense star formation and re-emits it as infrared radiation. Observing these galaxies in infrared allows astronomers to peer through the dust and uncover regions of vigorous star birth. These dusty, star-forming galaxies provide crucial insights into galaxy evolution and the early growth of the universe. By studying them, scientists gain a clearer picture of how stars and galaxies evolved across billions of years. Cosmic rays, high-energy particles from space, may subtly influence Earth's weather. These fast-moving particles, mostly protons, are accelerated by powerful cosmic events such as supernova and active galactic nuclei. When they strike Earth's atmosphere, they ionize atoms and molecules, creating showers of secondary particles. Some scientists propose that this ionization influences cloud formation, potentially affecting weather and climate patterns, though the exact impact remains debated. Cosmic rays represent a connection between distant cosmic events and Earth's atmospheric behavior. This link reminds us how deeply our planet is intertwined with the wider cosmos. The universe is dominated by matter, but why antimatter disappeared remains a great mystery. The Big Bang should have produced equal amounts of matter and antimatter, which annihilate each other upon contact. Yet, the universe today is overwhelmingly made of matter, with antimatter nearly absent. This imbalance, known as the baryon asymmetry, puzzles scientists. It suggests that some unknown process in the early universe favored matter's survival. Understanding this mystery is essential to explaining why anything exists at all. From galaxies and stars to planets and life, gravity leaves subtle marks on the ancient light we see today. As light travels through the cosmos, it passes near massive objects, such as galaxies and clusters, whose gravity bends and distorts its path. This phenomenon is called gravitational lensing. These tiny shifts imprint delicate distortions on the cosmic microwave background radiation, the oldest light we can detect. By studying these distortions, astronomers can map the distribution of visible matter as well as dark matter. Gravitational lensing offers a powerful tool for understanding the universe's structure and the invisible forces shaping it. Light traveling through space is gently bent and stretched by the gravity of massive objects. Massive celestial bodies such as galaxy clusters and black holes create gravitational fields strong enough to bend the path of light passing nearby. This bending, or gravitational lensing, can magnify and distort images of distant galaxies, sometimes creating arcs, rings, or even multiple images. This natural magnification acts like a cosmic telescope, enabling astronomers to observe galaxies too faint or too distant to otherwise detect. Gravitational lensing also provides a method for studying dark matter, which exerts gravity but emits no light, revealing the universe's hidden structure. The universe's first light began when stars and galaxies formed. After hundreds of millions of years of darkness following the Big Bang, the first stars ignited, ushering in the era of cosmic dawn. These pioneering stars grouped into young galaxies, their collective glow piercing the darkness and filling the cosmos with light for the first time. This ancient illumination marked a fundamental transformation, the end of the cosmic dark age. Ages and set in. Motion the processes that built the complex structures we see. Today, the universe became transparent when ultraviolet light ionized hydrogen gas. In its earliest years, the cosmos was a foggy expanse filled with neutral hydrogen gas that absorbed much of the light trying to travel through it. The formation of the first stars and galaxies changed this. Their ultraviolet radiation ionized the surrounding hydrogen, stripping electrons away and turning the gas into plasma. This phase of reionization cleared the fog, allowing light to stream freely across space. This transformation from opaque to transparent space opened a window for the cosmos to shine clearly, enabling the vast web of galaxies to emerge and be observed billions of years later. Star formation peaked billions of years ago, during a cosmic high noon. Billions of years in the past, the universe experienced an era of intense star formation, often called cosmic high noon. During this epoch, galaxies rapidly created stars at rates much higher than today. This surge enriched the universe with heavier elements essential for planets and life. After this peak, star formation gradually slowed, leading to the calmer cosmos we see now. This golden age shaped cosmic evolution, weaving the fabric of matter that supports galaxies, solar systems, and eventually life itself. Elements heavier than helium became more abundant as stars lived and died. The universe's earliest elements were mostly hydrogen and helium, produced during the Big Bang, but as stars formed and aged, they fused these light elements into heavier ones, such as carbon, oxygen, and iron in their cores. When massive stars exploded as supernova, they scattered these heavier elements into space, enriching the interstellar medium. This recycling process allowed later generations of stars and planets to form from richer material, eventually creating the building blocks of complex chemistry and life. Over billions of years, the universe transformed from a simple, primordial soup into a chemically diverse environment. Giant filaments of matter connect clusters of galaxies like threads in a cosmic web. The large-scale structure of the universe resembles a vast web, with clusters of galaxies linked by filaments stretching millions of light-years. These filaments, composed mainly of dark matter and gas, form the backbone of the cosmos, guiding the motion and growth of galaxies. Between them lie immense voids, regions of almost empty space. This cosmic web determines how galaxies cluster and evolve, revealing the universe's intricate architecture. Mapping these filaments helps scientists understand the distribution of matter and the forces sculpting the cosmos. Powerful jets of particles shoot out from supermassive black holes. At the centers of many galaxies lie black holes so massive that they can unleash jets of charged particles traveling at nearly the speed of light. These jets can extend millions of light years, shaping the gas and dust of their host galaxies. By heating and pushing material away, they regulate star formation and influence galactic evolution. Observing these energetic jets reveals the dynamic relationship between black holes and their environments, showcasing some of the universe's most powerful and dramatic phenomena. Massive galaxy clusters form the densest nodes of the cosmic web. These clusters are the largest gravitationally bound structures in the universe, containing hundreds or even thousands of galaxies packed into regions millions of light-years across. They act as the densest hubs within the sprawling cosmic web. Their immense gravity pulls galaxies together, influencing their motions, interactions, and growth. These clusters also contain vast amounts of hot, X-ray emitting gas, adding to their dynamic complexity. Studying galaxy clusters reveals how matter is distributed on the largest scales and provides clues about dark matter, dark energy, and the history of the universe. The universe's shape is incredibly close to flat, not curved like a sphere. Measurements show that the cosmos has astonishingly flat geometry, meaning it does not curve inward like a ball or outward like a saddle. This flatness implies a delicate balance between the total energy of the universe and its rate of expansion. In a flat cosmos, parallel lines stay parallel even across cosmic distances, shaping the paths of both light and matter. This discovery supports inflationary models that predicted such geometry and helps determine the universe's ultimate fate, suggesting expansion will continue rather than collapse. Understanding the shape of the universe is key to unraveling cosmic evolution. Tiny temperature differences in ancient light seeded all the structures we see today. The cosmic microwave background appears nearly uniform, but contains minute fluctuations of just a few millionths of a degree. These tiny ripples represent small density differences in the early universe. Over billions of years, gravity amplified these variations, causing matter to clump together into galaxies, clusters, and the grand web of cosmic structures. These ancient fluctuations are essentially the original blueprint of the universe, dictating how structures formed and evolved. Mapping them offers a window into the cosmos's infancy and the fundamental physics that shaped it. Some uncertainty in measurements arises because we observe only one universe. Cosmic variance is a fundamental limitation in cosmology, the result of having access to just one universe. Since we can only observe our unique cosmic environment, statistical studies of galaxy distributions or fluctuations in the cosmic background carry inherent uncertainties. Without multiple universes to compare, we cannot be sure whether the patterns we see are universal truths or simply chance occurrences. This uncertainty challenges astronomers to develop more refined models and careful analyses to reach strong conclusions. Cosmic variance reminds us of our unique vantage point and of the limits of our knowledge of the cosmos. Scientists estimate cosmic history by measuring the ages of distant galaxies. Astronomers use the light from faraway galaxies to determine their ages, effectively looking back in time by analyzing the stars inside those galaxies. And by studying their spectra, scientists can tell how long ago those galaxies began forming stars. Since light takes billions of years to reach us, observing distant galaxies reveals the history of the universe across vast epochs. These age estimates help build a timeline of cosmic events, including galaxy formation, star birth rates, and chemical evolution. Together with other data, measuring galaxy ages paints a detailed picture of how the universe grew from its earliest moments to the grand structures we see today. Hypothetical cosmic strings might be relics from the universe's earliest moments. These strings are theoretical, one-dimensional defects in space-time, predicted by some physics models of the early universe. Imagine ultra-thin but immensely dense filaments stretching across the cosmos, formed during phase transitions just fractions of a second after the Big Bang. If they exist, they could produce gravitational waves or distortions in the cosmic microwave background. Detecting such strings would provide deep insight into fundamental physics and into the conditions of the infant universe. Although no direct evidence has yet been found, cosmic strings remain a fascinating possibility, linking quantum physics with cosmic structure, high energy, X-rays glow from distant black holes, devouring matter. Deep within many galaxies lie supermassive black holes, often millions or billions of times the mass of our Sun. When these cosmic giants feed on surrounding gas and dust, the material forms a swirling accretion disk, heated to millions of degrees by friction and gravity. This extreme environment shines with powerful X-rays that travel billions of light years, detectable by space telescopes. These X-rays reveal the violent processes occurring near the event horizons of black holes. They help astronomers understand how black holes grow, how they influence galaxies, and the roles they play in shaping cosmic evolution. Observing these luminous beacons gives us a window into some of the universe's most mysterious realms. Turbulent gas clouds within galaxies shape the birth of stars. Vast clouds of gas, stirred by gravity. Shock waves from supernova and magnetic forces. Churn, turbulently. This turbulence compresses certain regions of the clouds, triggering the collapse of dense pockets that ignite as new stars. The balance between turbulence and gravity determines how many stars form and how massive they become. This intricate dance of chaos and calm governs the life cycle of galaxies. Understanding turbulence in these clouds is key to unraveling how galaxies evolve and sustain star formation across billions of years. Pulsars and distant galaxies send radio waves, filling the universe with invisible signals. Pulsars are rapidly spinning neutron stars, the remnants of massive star explosions, and they emit beams of radio waves sweeping through space like lighthouses. Alongside them, many galaxies emit diffused radio waves from energetic processes such as star formation and jets from black holes. Radio astronomy captures these signals, revealing hidden aspects of the universe, invisible light. These radio waves allow scientists to study exotic objects, to map magnetic fields, and to explore the large-scale structure of the cosmos. Listening to this invisible symphony reveals the dynamic energy of the pre-universe. Exploding stars launch particles that speed through space as cosmic rays. When massive stars end their lives in supernova explosions, they unleash shock waves that accelerate particles, mostly protons and atomic nuclei, close to the speed of light. These cosmic rays travel across the galaxy, sometimes reaching Earth's atmosphere and creating cascades of secondary particles. Detectable by instruments on the ground, they link Earth directly to violent events far away in the cosmos. Cosmic rays influence the chemistry and structure of the interstellar medium, and perhaps even Earth's atmosphere. They are messengers from some of the universe's most powerful events. Patterns in the polarization of ancient light reveal early cosmic events. The cosmic microwave background, the afterglow of the Big Bang, not only shines faintly, but also exhibits waves oscillating more in certain directions. This subtle polarization encodes information about gravitational waves and density ripples from the earliest moments of the universe. By studying these patterns, scientists test theories of cosmic inflation and learn how tiny quantum fluctuations grew into galaxies and clusters. These delicate signals provide a glimpse into the physics of the universe's birth and the forces that shaped its early evolution. Ultraviolet radiation cleared the cosmic fog, making the universe transparent. After the first stars formed, their ultraviolet light ionized the surrounding hydrogen gas that had once filled the universe with darkness. This process, called reionization, stripped electrons from hydrogen atoms, transforming the gas into plasma and turning the universe from an opaque haze into a transparent expanse where light could finally travel freely. This key transformation allowed light to journey vast distances, revealing galaxies and structures billions of years later. Reionization was a milestone in cosmic history, opening the window for the universe to shine. The first galaxies ionized hydrogen, transforming the early universe. As galaxies emerged, their intense ultraviolet light continued to ionize the hydrogen gas around them. This turned the universe from a neutral and foggy state into a transparent one, allowing light to cross space for the first time. This process not only illuminated the cosmos, but also revealed the large-scale structure of galaxies. The power of these early galaxies reshaped the universe, marking a major milestone in cosmic evolution. Studying this transition helps scientists understand how the first luminous objects paved the way for the complex structures of today. Dark energy's mysterious push is speeding up the universe's growth. Though gravity pulls matter together, a startling discovery showed that cosmic expansion is actually accelerating. Driven by dark energy, this mysterious force acts like a repulsive pressure, pushing galaxies farther apart, faster and faster. It accounts for about 70% of all the energy in the universe, yet remains one of the greatest puzzles in science. Its origin and its ultimate effect on the fate of the cosmos challenge our deepest understanding of physics. Will dark energy cause eternal expansion or lead to some unforeseen cosmic end? Unraveling its secrets remains one of the central quests of modern cosmology. The scale factor describes how distances in the universe expand over time. Cosmologists use this dimensionless number to track how space itself stretches as the universe grows. The scale factor changes. When it doubles, distances between galaxies also roughly double, illustrating cosmic expansion. Measuring the scale factor's changes helps scientists understand the history of expansion, the role of dark energy, and the dynamics of acceleration. This simple but powerful measure charts the unfolding of the universe across billions of years. The curvature of the universe influences its shape and destiny. Whether the universe is flat, open, or closed depends on the total density of matter and energy it contains. A flat universe means parallel lines remain parallel across cosmic distances, showing a balance between expansion and gravity. If it were curved inward like a sphere, it might eventually collapse. If it curved outward like a saddle, it would expand forever. Observations today show the universe is astonishingly close to flat. This insight guides our understanding of evolution, fate, and the paths of light and matter. Matter is distributed evenly across the largest scales. When viewed on scales spanning hundreds of millions of light years, matter, including galaxies and dark matter, appears remarkably uniform. This homogeneity means no vast region is significantly denser or emptier than another, simplifying cosmological models and supporting the cosmological principle that the universe is isotropic and homogeneous. Though locally galaxies form clusters and voids exist, the overall balance reveals the deep symmetries governing cosmic evolution. The universe looks nearly the same in every direction. This cosmic isotropy, together with homogeneity, forms the foundation of modern cosmology. Observations, including of the cosmic microwave background, show that temperature and matter distribution remain nearly uniform across the sky. This suggests that the laws of physics are consistent everywhere, allowing universal models of history, expansion, an evolution to be built. The discovery of cosmic background radiation confirmed the Big Bang in 1965. Scientists Arno Penzias and Robert Wilson accidentally discovered a faint, uniform microwave glow permeating the universe, now known as the cosmic microwave background radiation. This ancient light is the afterglow of the Big Bang, dating back nearly 14 billion years to the time when the universe first became transparent. Its discovery provided powerful evidence for the Big Bang theory, transforming cosmology from speculation into science. Detailed measurements of this radiation revealed tiny fluctuations in temperature, the seeds of galaxies and the structures of the cosmos. The cosmic microwave background remains a cornerstone of modern understanding, a time capsule from the universe's infancy and a guide to its evolution. Cosmic history spans from fractions of a second to billions of years. The universe's story began in an unimaginably brief instant, the Planck epoch, just a fraction of a second after the Big Bang. From this fiery birth, cosmic history unfolded in states of recombination, cosmic dawn, and galaxy formation. Each era brought profound changes. Space expanded, matter cooled, light emerged, and structures formed. Billions of years passed as galaxies evolved, stars ignited, and planets took shape. This immense timeline reveals a universe in constant transformation, where every moment connects past, present, and future in an ongoing cosmic dance. Understanding this timeline helps us grasp our place in the grand story. The observable universe grows as the cosmic light horizon expands. The observable universe is bounded by the cosmic light horizon, the farthest distance from which light has reached us since the Big Bang. As time passes, this horizon slowly expands, allowing us to see more distant galaxies and structures. However, due to cosmic expansion, some regions may remain forever beyond our reach. The expanding horizon represents the limits of human observation and knowledge. It is a reminder that although we have glimpsed incredible cosmic depths, much of the universe remains hidden in silence, waiting patiently for future discoveries. Brief, powerful bursts of energy light up space for moments at a time. Gamma-ray bursts are intense flashes of high-energy radiation that can outshine entire galaxies for mere seconds or minutes. They often result from the collapse of massive stars or from merging neutron stars. Despite their fleeting nature, gamma-ray bursts release tremendous energy, illuminating the far reaches of the cosmos. They serve as cosmic beacons, offering clues about stellar deaths, black hole formation, and the evolution of the universe. Observing these short-lived events allows scientists to probe extreme physics under conditions impossible to recreate on Earth. Expanding space stretches the light traveling through it. As the universe expands, light waves moving through space are stretched, increasing their wavelength in a process known as cosmological redshift. This stretching shifts light toward the red end of the spectrum, making distant galaxies appear redder than they originally emitted. Redshift functions as a cosmic clock, letting astronomers measure how fast galaxies recede and estimate their distances. It provides direct evidence of cosmic expansion and allows us to look back in time, seeing galaxies as they were billions of years ago. This subtle stretching of light is a profound signature of the universe's growth. Relic neutrinos have filled space since the universe was only 1 second old, almost immediately after the Big Bang. The cosmos was flooded with neutrinos, tiny, nearly massless particles that rarely interact with matter. These relic neutrinos decoupled from the hot plasma within the first second and have been streaming through space ever since. Though extremely difficult to detect, they influence cosmic evolution and the formation of large-scale structures. They are fossils of the early universe, carrying information about its first moments. Detecting and studying them remains a great goal of physics, promising insight into the fundamental nature of the cosmos. Cosmic voids are giant empty regions between galaxy clusters. These vast, sparsely populated areas stretch millions of light-years across, like cosmic deserts between the denser galaxy clusters and filaments. Though they contain very little matter, they play a crucial role in shaping the universe's large-scale structure. Their low density pushes surrounding galaxies outward, influencing how matter flows through the cosmic web. Studying voids helps scientists understand the distribution of dark matter, the effects of dark energy, and the balance of cosmic forces. These silent expanses remind us of the vastness of space and of the delicate balance between matter and emptiness. Galaxies grow larger through slow mergers over billions of years. They are dynamic systems that evolve by merging with neighbors. These mergers are slow, majestic processes that unfold across eons as stars, gas, and dark matter gradually combine. Such mergers can trigger bursts of star formation, reshape galactic structures, and fuel the growth of central black holes. Our own Milky Way is expected to collide and merge with the Andromeda Galaxy in several billion years. Studying these processes reveals how complexity builds over time, painting a picture of a universe always in transformation. Invisible magnetic fields thread through galaxies, guiding charged particles. Though unseen, these magnetic forces influence many cosmic processes. They guide the motion of particles, affect the birth of stars, and shape the behavior of interstellar gas. Galactic magnetic fields, though far weaker than Earth's, extend thousands of light years, weaving through spiral arms and halos. Studying these invisible structures helps astronomers understand the dynamics of galaxies, the journey of cosmic rays, and the balance between matter and energy on cosmic scales. These unseen threads add depth to the universe's fabric. Cosmic rays occasionally cause mutations in DNA here on Earth. These energetic particles, born from supernova and other cosmic events, can reach the surface after colliding in Earth's atmosphere. Some penetrate living organisms, where they occasionally alter DNA, while most mutations are harmless or repaired. Some contribute to genetic variation and even evolution. The constant rain of cosmic rays links Earth's biological history to the wider cosmos, showing how distant events subtly influence life. Here, bubble-like structures may have formed during early cosmic phase transitions. In the universe's earliest instance, rapid changes called phase transitions may have created bubble-like regions in spacetime. These bubbles could have expanded, collided, and left imprints on the cosmic microwave background, or even produced gravitational waves. Such transitions are tied to the separation of fundamental forces as the universe cooled. Detecting signs of these bubbles would provide insight into high-energy physics and the conditions just after the Big Bang, offering a glimpse into the fiery birth of the cosmos. Tiny fluctuations in ancient light reveal our universe's beginnings. The cosmic microwave background carries faint ripples, tiny temperature and density variations that were the seeds of all structures. These differences, though incredibly small, were amplified by gravity across billions of years into galaxies, clusters, and filaments. Mapping these ripples with precision allows scientists to decode the conditions of the early universe and test cosmological theories. These delicate imprints are a profound window into the cosmos's origins. Cosmic rays help create the northern and southern lights near Earth's poles. The auroras, those shimmering curtains of green, red, and purple light, are partly sparked by cosmic rays. When high-energy particles collide with Earth's magnetic field and atmosphere near the poles, they excite gases that glow in vivid colors. Alongside the solar wind, cosmic rays energize the upper atmosphere, producing these beautiful displays. The auroras are a reminder that our planet is deeply connected to the energetic events of the cosmos. Galaxies flow along gravitational currents shaped by matter's distribution. They do not drift randomly, but move along vast, invisible flows defined by dark matter. These gravitational streams guide galaxies along the filaments of the cosmic web, pulling them toward dense clusters and away from voids. This flow influences how galaxies evolve and interact across billions of years. By mapping these streams, astronomers uncover the forces that drive cosmic evolution, revealing the universe's deep interconnectedness. Approximately 380,000 years after the Big Bang, photons decoupled from matter and traveled freely. This event, called recombination, marked the release of the cosmic microwave background, the oldest light we can see today. Before this, the universe was opaque, with photons constantly scattering off charged particles. But once the cosmos cooled enough for atoms to form, light was freed to travel across space and time. This moment transformed the universe into a transparent expanse, and the ancient light that emerged still carries information about those early conditions. Though, locally, galaxies form clusters and voids exist, the overall balance reveals the deep symmetries governing cosmic evolution. The universe looks nearly the same in every direction. This cosmic isotropy, together with homogeneity, forms the foundation of modern cosmology. The discovery of cosmic background radiation confirmed the Big Bang. In 1965, scientists Arno Penzias and Robert Wilson accidentally discovered a faint, uniform microwave glow permeating the universe. Now known as the cosmic microwave background radiation, this ancient light is the afterglow of the Big Bang, dating back nearly 14 billion years to the time when the universe first became transparent. Its discovery provided powerful evidence for the Big Bang theory, transforming cosmology from speculation into science. Detailed measurements of this radiation revealed tiny fluctuations in temperature, the seeds of galaxies, and the structures of the cosmos. The cosmic microwave background remains a cornerstone of modern understanding, a time capsule from the universe's infancy and a guide to its evolution. Cosmic history spans from fractions of a second to billions of years. The universe's story began in an unimaginably brief instant, the Planck epoch, just a fraction of a second after the Big Bang. From this fiery birth, cosmic history unfolded in recombination, cosmic dawn, and galaxy formation. Each era brought profound changes. Space expanded, matter cooled, light emerged, and structures formed. Billions of years passed as galaxies evolved, stars ignited, and planets took shape. This immense timeline reveals a universe in constant transformation, where every moment connects past, present, and future in an ongoing cosmic dance. Understanding this timeline helps us grasp our place in the grand story. The observable universe grows as the cosmic light horizon expands. The observable universe is bounded by the cosmic light horizon, the farthest distance from which light has reached us since the Big Bang. As time passes, this horizon slowly expands, allowing us to see more distant galaxies and structures. However, due to cosmic expansion, some regions may remain forever beyond our reach. The expanding horizon represents the limits of human observation and knowledge. It is a reminder that although we have glimpsed incredible cosmic depths, much of the universe remains hidden in silence, waiting patiently for future discoveries. Brief, powerful bursts of energy light up space for moments at a time. Gamma-ray bursts are intense flashes of high-energy radiation that can outshine entire galaxies for mere seconds or minutes. They often result from the collapse of massive stars or from merging neutron stars. Despite their fleeting nature, gamma-ray bursts release tremendous energy, illuminating the far reaches of the cosmos. They serve as cosmic beacons, offering clues about stellar deaths, black hole formation, and the evolution of the universe. Observing these short-lived events allows scientists to probe extreme physics under conditions impossible to recreate on Earth. Expanding space stretches the light traveling through it. As the universe expands, light waves moving through space are stretched, increasing their wavelength in a process known as cosmological redshift. This stretching shifts light toward the red end of the spectrum, making distant galaxies appear redder than they originally emitted. Redshift functions as a cosmic clock, letting astronomers measure how fast galaxies recede and estimate their distances. It provides direct evidence of cosmic expansion and allows us to look back in time, seeing galaxies as they were billions of years ago. This subtle stretching of light is a profound signature of the universe's growth. Relic neutrinos have filled space since the universe was only 1 second old. Almost immediately after the Big Bang, the cosmos was flooded with neutrinos, tiny, nearly massless particles that rarely interact with matter. These relic neutrinos decoupled from the hot plasma within the first second and have been streaming through space ever since. Though extremely difficult to detect, they influence cosmic evolution and the formation of large-scale structures. They are fossils of the early universe, carrying information about its first moments. Detecting and studying them remains a great goal of physics, promising insight into the fundamental nature of the cosmos. Cosmic voids are giant empty regions between galaxy clusters. These vast, sparsely populated areas stretch millions of light-years across, like cosmic deserts between the denser galaxy clusters and filaments. Though they contain very little matter, they play a crucial role in shaping the universe's large-scale structure. Their low density pushes surrounding galaxies outward, influencing how matter flows through the cosmic web. Studying voids helps scientists understand the distribution of dark matter, the effects of dark energy, and the balance of cosmic forces. These silent expanses remind us of the vastness of space and of the delicate balance between matter and emptiness. Galaxies grow larger through slow mergers over billions of years. They are dynamic systems that evolve by merging with neighbors. These mergers are slow, majestic processes that unfold across eons as stars, gas, and dark matter gradually combine. Such mergers can trigger bursts of star formation, reshape galactic structures, and fuel the growth of central black holes. Our own Milky Way is expected to collide and merge with the Andromeda Galaxy in several billion years. Studying these processes reveals how complexity builds over time, painting a picture of a universe always in transformation. Invisible magnetic fields thread through galaxies, guiding charged particles. Though unseen, these magnetic forces influence many cosmic processes. They guide the motion of particles, affect the birth of stars, and shape the behavior of interstellar gas. Galactic magnetic fields, though far weaker than Earth's, extend thousands of light years, weaving through spiral arms and halos. Studying these invisible structures helps astronomers understand the dynamics of galaxies, the journey of cosmic rays, and the balance between matter and energy on cosmic scales. These unseen threads add depth to the universe's fabric. Cosmic rays occasionally cause mutations in DNA here on Earth. These energetic particles, born from supernova and other cosmic events, can reach the surface after colliding in Earth's atmosphere. Some penetrate living organisms, where they occasionally alter DNA, while most mutations are harmless or repaired. Some contribute to genetic variation and even evolution. The constant rain of cosmic rays links Earth's biological history to the wider cosmos, showing how distant events subtly influence life. Here, bubble-like structures may have formed during early cosmic phase transitions. In the universe's earliest instance, rapid changes called phase transitions may have created bubble-like regions in space-time. These bubbles could have expanded, collided, and left imprints on the cosmic microwave background, or even produced gravitational waves. Such transitions are tied to the separation of fundamental forces as the universe cooled. Detecting signs of these bubbles would provide insight into high-energy physics and the conditions just after the Big Bang, offering a glimpse into the fiery birth of the cosmos. Tiny fluctuations in ancient light reveal our universe's beginnings. The cosmic microwave background carries faint ripples, tiny temperature and density variations that were the seeds of all structures. These differences, though incredibly small, were amplified by gravity across billions of years into galaxies, clusters, and filaments. Mapping these ripples with precision allows scientists to decode the conditions of the early universe and test cosmological theories. These delicate imprints are a profound window into the cosmos's origins. Cosmic rays help create the northern and southern lights near Earth's poles. The auroras, those shimmering curtains of green, red, and purple light, are partly sparked by cosmic rays. When high-energy particles collide with Earth's magnetic field and atmosphere near the poles, they excite gases that glow in vivid colors. Alongside the solar wind, cosmic rays energize the upper atmosphere, producing these beautiful displays. The auroras are a reminder that our planet is deeply connected to the energetic events of the cosmos. Galaxies flow along gravitational currents shaped by matter's distribution. They do not drift randomly, but move along vast, invisible flows defined by dark matter. These gravitational streams guide galaxies along the filaments of the cosmic web, pulling them toward dense clusters and away from voids. This flow influences how galaxies evolve and interact across billions of years. By mapping these streams, astronomers uncover the forces that drive cosmic evolution, revealing the universe's deep interconnectedness. Approximately 380,000 years after the Big Bang, photons decoupled from matter and traveled freely. This event, called recombination, marked the release of the cosmic microwave background, the oldest light we can see today. Before this, the universe was opaque, with photons constantly scattering off charged particles. But once the cosmos cooled enough for atoms to form, light was free to travel across space and time. This moment transformed the universe into a transparent expanse, and the ancient light that emerged still carries information about those early conditions. Small temperature variations in ancient light seeded galaxies and clusters. The cosmic microwave background is almost uniform, but it carries tiny differences in temperature, mere millionths of a degree. These subtle fluctuations represent small variations in matter density in the young universe. Over billions of years, gravity amplified them, leading matter to clump into galaxies, clusters, and the cosmic web. These primordial seeds set the stage for the large-scale structure of the cosmos. By mapping these temperature variations with precision, scientists gain insight into the universe's infancy and the processes that guided its growth. Gravitational tides stretch and shape galaxies over time. Just as the moon's pull creates tides on Earth, gravitational forces from nearby galaxies and from dark matter create tidal effects in galaxies themselves. These cosmic tides stretch, distort, and reshape galaxies, influencing their spiral arms and their patterns of star formation. Over millions of years, these interactions can trigger bursts of star birth, or even lead to galactic mergers. Studying these tidal forces reveals how galaxies evolve within their environments, and highlights the dynamic and interconnected nature of the universe. Quantum fluctuations during inflation grew into galaxies and clusters. In the brief period of cosmic inflation just after the Big Bang, tiny variations in energy at the quantum scale were stretched to cosmic proportions. These fluctuations became the seeds from which all galaxies and clusters grew. Inflation magnified these minute ripples, imprinting them onto the fabric of space-time itself. Over billions of years, gravity shaped them into the grand cosmic structures we see today. This extraordinary process connects the smallest scales of the quantum world to the largest scales of the cosmos, revealing the deep unity of nature. Cosmic dust grains are the seeds from which stars and planets form. Tiny specks of dust, made of carbon, silicon, and metals, drift through interstellar space. These grains gather in immense clouds, cooling the gas and allowing it to collapse under gravity. This collapse sparks the birth of new stars, while the surrounding dust collects into disks that eventually form planets, moons, and other celestial bodies. Dust also supports chemical reactions, helping to create complex molecules essential for life. Though minuscule, these grains are the building blocks of stars, worlds, and the fabric of the cosmos itself. Light years measure distances too vast for ordinary units. A light year is the distance light travels in 1 year, about 6 trillion miles or 10 trillion kilometers. This unit provides a simple way to describe cosmic distances. The nearest star beyond our sun is over 4 light years away, meaning its light takes more than 4 years to reach us. Light-years link distance to time, allowing us to grasp the immensity of the cosmos and the speed of light's long journey through space. The universe's oldest light has a temperature just a few degrees above absolute zero. The cosmic microwave background radiation fills all of space with a temperature of about 2.7 degrees above absolute zero. This faint glow is the cooled remnant of the hot, dense, early universe. As the cosmos expanded over billions of years, this light stretched and cooled, Its nearly uniform temperature carries small ripples that seeded cosmic structures. This cold, dim glow is a silent reminder of how the universe has evolved from fiery beginnings to its present vast, cool state. Cosmic ray showers cascade through Earth's atmosphere constantly. High-energy particles, traveling close to light speed, strike Earth's atmosphere, colliding with atoms and creating cascades of secondary particles called air showers. These showers spread through the atmosphere, sometimes reaching Earth's surface, where they are detected by instruments worldwide. Cosmic ray showers offer insights into the universe's most energetic events, such as supernova and black hole jets. They also interact with the atmosphere, perhaps even influencing climate patterns. This constant shower of particles is a reminder of Earth's connection to the wider cosmos. Voids influence the movement and growth of galaxies around them. These immense regions, with few galaxies, shape the dynamics of their surroundings. Their low density pushes surrounding matter outward, guiding galaxies along the filaments of the cosmic web. In this way, voids shape both the flow of matter and the formation of structures. Studying voids helps astronomers understand dark energy, dark matter, and the large-scale evolution of the universe. Though empty, they play a vital role in the balance of cosmic growth. Jets from black holes sculpt their host galaxies. Supermassive black holes at galactic centers often unleash jets of particles, moving close to light speed. These jets can extend millions of light years, heating and dispersing the gas around them. By regulating star formation and reshaping the interstellar medium, they act as cosmic sculptors, shaping the growth of their galaxies. Observing these jets reveals the complex interplay between black holes and galaxies, offering insight into some of the universe's most powerful processes. The first galaxies formed during a time known as cosmic dawn. After hundreds of millions of years of darkness, primordial clouds of gas collapsed under gravity, giving birth to the earliest stars and galaxies. These young galaxies flooded the universe with ultraviolet light, beginning the process of reionization and transforming the cosmic landscape. This dawn marked the end of the dark ages and the beginning of the universe's luminous chapter. Studying this period helps us understand how the simplest building blocks grew into the complex cosmic structures of today. The universe's oldest light fills space almost uniformly. The cosmic microwave background glows faintly across the entire sky, a relic from when the universe first became transparent nearly 14 billion years ago. Its temperature varies by only tiny fractions of a degree, reflecting the smoothness of the early cosmos before gravity amplified its ripples into galaxies and clusters. This pervasive glow is a silent witness to the universe's infancy, a cosmic backdrop that links us directly to its origins. Measuring galaxy ages helps scientists chart the universe's history. By analyzing the light of galaxies billions of light years away, scientists can look back in time and estimate their ages. Spectral signatures reveal the ages of stars inside them, offering clues about when star formation began and how galaxies evolved. This method of cosmic archaeology creates a timeline of galaxy growth, chemical enrichment, and star birth rates. Together with other observations, measuring galaxy ages reveals the story of how matter evolved from a hot, dense beginning to the complex structures we see now. Cosmic evolution describes how everything changes across billions of years. It is the grand narrative of transformation from the fiery inception of the universe to its present form. It includes the formation of stars, galaxies, and planets, and the rise of chemical complexity. Over time, fundamental forces shaped matter and energy into intricate patterns. This continual change is reflected in galaxies, star populations, and cosmic environments. Understanding cosmic evolution helps us see our place in this dynamic universe, always growing and unfolding its secrets. Cosmic variance reminds us that we can observe only one universe. This limit means we cannot perform multiple trials, as in laboratory science. Astronomers must rely on the one cosmos we inhabit. As a result, measurements of the microwave background or of galaxy clustering carry uncertainties that may reflect random chance, rather than universal truths. This humbling limit challenges scientists to separate signal from noise and reminds us of the unique perspective humanity holds. Cosmic rays interact with the solar wind flowing from the sun. The solar wind, a constant stream of charged particles, collides with incoming cosmic rays, shaping how many reach Earth. This interaction modulates cosmic ray intensity, influencing the upper atmosphere and contributing to space weather. Changes in solar activity alter this modulation, varying the flow of cosmic rays over time. Understanding this relationship is crucial for protecting satellites, astronauts, and technology from radiation. It also shows how our star connects with cosmic influences from beyond. Magnetic fields stretch across entire galaxies, shaping their growth. These unseen fields guide the flow of charged particles and gas, influencing how stars form. They span thousands of light, threading through spiral arms and halos, weaving a hidden structure into galactic life. Though weaker than Earth's magnetic field, their scale gives them great influence. Studying them helps astronomers understand galactic dynamics, cosmic rays, and the balance of forces shaping the universe. Reionization made the universe transparent to ultraviolet light. In its infancy, the cosmos was filled with neutral hydrogen gas that absorbed ultraviolet light, making space dark and opaque. The first stars and galaxies emitted intense ultraviolet radiation that ionized this hydrogen, stripping electrons away and transforming the gas into plasma. This epoch of reionization lifted the cosmic fog, allowing light to travel freely for the first time. This transformation changed the appearance of the universe forever, revealing galaxies and structures across billions of years. Studying reionization helps scientists understand how the earliest luminous objects cleared the cosmic haze. Cosmic dawn ended the universe's dark and opaque childhood. Before this time, the cosmos was shrouded in hydrogen gas, which absorbed and blocked light. The birth of the first stars and galaxies brought intense radiation that ionized the hydrogen, clearing the fog and allowing light to shine across the vast expanse. This dawn of illumination turned the universe into the transparent cosmos we see today. Exploring cosmic dawn helps astronomers understand when and how the universe first lit up. Cosmic strings, if they exist, could reveal secrets of fundamental physics. These ultra-thin defects in space-time are hypothetical objects predicted by theories of the early universe. If real, these incredibly dense filaments could stretch across vast distances, altering gravitational fields and perhaps producing detectable waves. Detecting them would provide profound insights into the unification of forces and the structure of space-time itself, though no direct evidence exists. Cosmic strings remain a fascinating idea that could bridge the smallest scales of quantum mechanics with the largest scales of cosmology. Inflation explains why the universe appears smooth and uniform on large scales. The theory of cosmic inflation proposes that the universe underwent a brief period of exponential expansion. Moments after the Big Bang, this rapid stretching smoothed out irregularities, distributing tiny quantum fluctuations across vast regions of space. Inflation explains why the cosmos looks so uniform in every direction. Despite its immense size, those small fluctuations became the seeds of galaxies and structures. Inflation solves several puzzles in cosmology and remains a cornerstone of modern understanding, linking quantum physics with the grandest cosmic patterns. Photons from the Big Bang carry messages from the universe's birth. These particles of light, released during the first moments, have been traveling through space for nearly 14 billion years. They form the cosmic microwave background, a faint glow that fills the sky. Their properties carry information about the early universe, its composition, and its growth. By studying these photons, scientists uncover the secrets of cosmic origin, inflation, and structure. They are messengers from the dawn of time, connecting us directly to the fiery birth of the universe. Cosmic rays were first discovered more than a century ago. In the early 1900s, scientists noticed mysterious radiation penetrating Earth's atmosphere. Eventually, it was identified as cosmic rays, high-energy particles arriving from space. These particles, mostly protons and atomic nuclei, travel at near light speed and strike Earth constantly. Early experiments by Victor Hess showed that the radiation increased at higher altitudes, proving its extraterrestrial origin. Since then, cosmic rays have intrigued scientists, offering clues about supernova, black hole jets, and other violent events. Their discovery opened a new chapter in physics, linking Earth to the energetic processes of the wider cosmos. Cosmic horizons limit how far we can see into space and time. The universe is about 13.8 billion years old, meaning light from beyond a certain distance has not yet reached us. This cosmic horizon defines the edge of the observable universe. Beyond it may lie countless galaxies and mysteries, but they remain forever hidden. As time passes, the horizon slowly expands, revealing more distant regions. Yet due to expansion, some areas may always remain unreachable. The horizon sets a limit on human knowledge, reminding us that the cosmos is larger than we can ever see. The cosmic microwave background captures a snapshot of the young universe. This faint, uniform glow fills all of space. A relic from about 380,000 years after the Big Bang. At that time, the universe cooled enough for photons to travel freely, creating a visible snapshot of its infancy. Subtle fluctuations in this radiation reflect density differences that seeded galaxies and cosmic structures. Detailed observations of the microwave background provide insights into composition, age, and evolution. It remains one of the most important pillars of modern cosmology. Polarization in ancient light helps reveal the universe's earliest moments. Beyond its temperature, the cosmic microwave background also shows polarization patterns in the orientation of light waves. These patterns encode information about gravitational waves and density ripples from the first instance of time. Studying them allows scientists to test models of inflation and trace how tiny fluctuations grew into galaxies and clusters. Polarization measurements open the window into the physics of the Big Bang itself. Cosmic filaments contain much of the universe's ordinary matter. Galaxies cluster along vast filaments composed of dark matter and baryonic matter, such as gas and dust, stretching millions of light years. These structures form the backbone of the cosmos. Though dark matter dominates, the filaments also hold much of the ordinary matter that forms stars, planets, and life. This matter exists as hot, diffuse gas between galaxies, often hard to detect. Studying filaments helps trace how matter flows through the universe and how galaxies grow within this immense network. Jets from black holes can stretch for millions of light years. Supermassive black holes at the centers of galaxies often launch jets of particles moving at nearly light speed. These jets sculpt the intergalactic medium and regulate star formation by heating and displacing gas. They can either suppress star birth or trigger new bursts. Observing such colossal jets reveals the powerful interplay between black holes and their environments. Some of the most dramatic processes in the universe. Inflation left subtle imprints on ancient light we see today. During that brief moment of rapid expansion, quantum ripples were stretched into large-scale structures. These fluctuations became the seeds of galaxies, clusters, and filaments. Their imprint remains in the cosmic microwave background as faint variations in temperature and polarization. By studying these delicate patterns, scientists gain insights into the physics of the universe's birth. Linking the quantum realm with the cosmic stage, cosmic rays may play a role in Earth's cloud formation. Some scientists suggest that cosmic rays influence climate by seeding cloud droplets. When these high-energy particles enter Earth's atmosphere, they ionize molecules, producing charged particles that can trigger condensation. Clouds, in turn, reflect sunlight and trap heat. Although the extent of this effect is debated, cosmic rays may connect distant stellar events with Earth's weather. This possibility highlights the subtle ties between space and our planet's environment. Galactic movements follow the path set by cosmic filaments. Galaxies do not wander aimlessly, but flow along gravitational currents defined by the cosmic web. These vast strands of dark matter and gas draw galaxies toward clusters and away from voids, shaping their interactions and growth. Over billions of years, these flows direct the structure of the universe. Mapping these cosmic highways helps astronomers understand the forces that sculpt galaxies and the grand architecture of space itself. Neutrinos offer clues about the universe's very beginnings. These nearly massless particles were produced in enormous numbers in the first seconds after the Big Bang. They decoupled from matter almost immediately and have streamed through space ever since, barely interacting with anything. Though elusive, they carry precious information about the early universe and fundamental physics. By studying neutrinos, scientists probe conditions otherwise beyond reach, opening a unique window into the cosmos's birth and its underlying laws. And now, the vastness of the cosmos begins to gently fade behind your thoughts. You have drifted through countless wonders, from the brilliance of newborn stars to the shadows of ancient galaxies, from the web of dark matter to the whispers of ancient light. You have traveled through stellar nurseries, glided along spiral arms, and glimpsed the heart of the universe glowing softly across unimaginable distances. You are part of this cosmic story. Not just an observer, but a participant woven from stardust and time. The atoms in your body were forged in the fires of ancient stars. The air you breathe carries the memory of explosions long past. Everything within you shares its origin with the universe itself. Born from the same primordial matter that flows through galaxies and drifts in clouds between the stars. Tonight, as you rest, the cosmos continues its quiet unfolding. Stars are forming, light is traveling, Galaxies are dancing in silence. You are a small, warm presence within this vast, radiant sea, peacefully floating among the stars. Thank you for journeying through the cosmos tonight. I hope you sleep well and dream softly. Good night.